For a while now, we're going to focus on exponents and the things that you can do with them. So we're going to start with some rules and see how you go with them. Let's start with the following. Everybody knows that if I take 3 to the second power, that means 3 times 3, which is 9. 3 to the third power equals 3 times 3 times 3, which is 27. 3 to the fourth power is 3 times 3 times 3 times 3, which is 81, and etc. One that I didn't write was this one. 3 to the 1 power is simply 3. So the exponent shows how many of them appear in the multiplication process. So in general, if I take some number and raise it to the nth power, I'm going to have x times x times x, and that will go on all the way until I've used up n x's. So there's n times that I'm multiplying x together. So what do we have here? Let's take a look at an x to the n. That thing up there is called the exponent. This quantity x is called the base. So I'll make use of those terms liberally throughout the proceedings. Just as a quick example, and to show you some pitfalls that are possibly there already, I have, most people know squares, like 5 squared is 5 times 5, that's 25. Make sure that you can find your exponent key on your calculator, because if I have you do 5 to the third power, that's 5 times 5 times 5. Your calculator may not have a button for the third power. I know they'll have an x squared button, but they may not have an x to the third button. So make sure you can find that. Typically, on a lot of calculators, you may see something like 5, and then you'll see a button like y to the x. And then I would hit a 3, and then the equals. That would be one way. Some calculators do it that way. You might have the x and the y switched in there. It really doesn't matter. Some of your calculators may require you to use this thing, this little caret button, 3, and then equals, and they'll give you the same answer either way. So make sure you find the appropriate button on your calculator. Let's do some of these. Here's ones that will get complicated. If I have negative 2 to the fourth, that's the same as negative 2 times negative 2 times negative 2 times negative 2. Well, you have 4 negatives. When you multiply 4 negatives together, it turns into a positive. And so we have positive 2 to the fourth, which is 2, 4, 8, 16, which is positive 16. Compare it with negative 2 to the fourth. This is not equal to 16. The way we can think of it is that negative 2 to the fourth power is negative 1 times 2 to the fourth. The lack of a parenthesis allows me to bring the negative out like that. Now, what you would do, according to PEMDAS, is you would do the exponent first. So you get negative 1 times 16. And so this answer is actually negative 16. Notice that if I do negative 2 to the third, I'll get negative 2 times negative 2 times negative 2. And that will end up being negative 8 because you're multiplying 3 negative numbers together. But now compare it with negative 2 to the third power, which is the same as negative 1 times 2 to the third. You would do the 2 to the third first, so you'd have negative 1 times 8 equals negative 8. So for those situations where the exponent is odd, it's not going to make any difference. You're going to get a negative answer. But it's the even ones you got to be careful with. Even exponents. Be careful with this. Sometimes it's positive and sometimes it's negative. Make sure that you're able to tell which one is which. Alright, so let me do some more examples. This was just a warning to you. We already did to the odd exponents and things of that nature, so let's move on to some fractions. Let's try 4/5 to the third power. So here we're going to have 4/5 times 4/5 times 4/5. And when you multiply these all together, you multiply the numerators together and you multiply the denominators together. You'll notice that the exponent will carry through to the numerator and the denominator, just like that. 4 to the third is 64. 5 to the third is 125. Let's try some other examples. Let's try 2 to the third times 2 to the fourth. So we'll do the 2 to the third first. Right there is the 2 to the third. And now I'm going to do the 2 to the fourth. There's the 2 to the fourth. Well, if you look at there's a total of, let's see, 1, 2, 3, 4, 5, 6, 7 2's. So it's actually the same as 2 to the 7th. So what I have is 2 to the third times 2 to the fourth is 2 to the 7th. Let me do another example. Let me do 3 squared times 3 to the 5th power. So 3 squared is 3 times 3, and 3 to the 5th, I'll have 5 of these things. So you can see them. There's 3 squared right there in front, and then there's 3 to the 5th. Well, there's a total of 1, 2, 3, 4, 5, 6, 7 3's. So this is the same as 3 to the 7th power. So hopefully you're seeing a pattern here. We have 2 to the third, well, 2 to the third, times 2 to the fourth. 2 to the third times 2 to the fourth is 2 to the 3 plus 4. Down here, 3 squared times 3 to the 5th equals 3 to the 2 plus 5. I realize that this makes it look like it only works for 7, so let me invent one more. I'll have 5 squared times 5 to the 9th. So the 5 squared will be 2 of them, and 5 to the 9th I'll have 9 more. 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many 5's do we have altogether then? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 5 raised to the 11th power. So what we had then was we had 5 squared times 5 to the 9th is 5 to the 2 plus 9. So that, of course, gives us a general rule for the product of two numbers with the same base. So we have, let me put the rule down here. If I have x to the m power times x to the n power, we can write it as x to the m plus n. So this is something like a product rule. I'll give you the names of these at the end of this. But as I'm developing, I just want you to use them and become comfortable with them. So we can do a little mixing of things. If I give you something like the following. Suppose I ask you to simplify. And you're given 3x squared times 5x to the fourth. Well, what you can do is you can multiply the numbers together. You've already done some of this stuff. The 3 and the 5 gives us the 15. But then the x, I'll do 2 plus 4 because I had x in both situations there. One was raised to the second, one was raised to the fourth. So I get 15x to the 6th. I think for most of these, it's probably easier to do them with y's than anything else. Here's a weird example. Not y's, but letters. It's actually easier to do letters with some of these rules than it is with numbers, because numbers you can combine, and where they came from disappears once you combine them. So for this, the entire base is negative y. So you're going to have negative y to the 5 plus 3. That's the same as negative y to the 8th. And the negative, because you're going to be multiplying y by itself 8 times, those negatives will all cancel, and you can simply write it as y to the 8th power. Now, you need to be careful here. All these rules require that you have the same base. So if I tried to do 2 to the 3rd times 5 to the 4th, for example, there's no rule for that. So I can't combine those exponents or anything. It's important that this rule that I specified up here, this rule here, is that you have the same bases. That's crucial for this rule to work. All right, anyways, let me go on to more examples and more rules. Here's another one. Suppose I have a number raised to a power, but that whole thing is also raised to a power. Now, according to the rules of exponents, you're supposed to do, or the order of operations, you're supposed to do the exponent first here, or you're supposed to do in the parentheses first. So you would do 2 to the 3rd, which would be 8 to the 4th power, and then you have 64 times 64. This is what I was talking about. This obscures the rule that I want to talk about. Instead, let me do this rule. Suppose I have x to the 3rd raised to the 4th power. Now, inside of the parentheses, it's already done. So what I can do here is write x to the 3rd times x to the 3rd times x to the 3rd times x to the 3rd. So there's 4 of them. That's raising it to the 4th power. But using the rule that we just did a minute ago, I'm going to add up all those exponents. And then you're going to end up with x to the 12th. But really, when you were first learning how to do multiplication, they probably taught you that multiplication was a fast way of doing addition. So these 3's, there's 4 3's made up a 12. What I actually did was this: x to the 3rd to the 4th power, I can rewrite as x to the 3rd times 4th. That's why I had those 4 3's up there. That was the same as 4 times 3. So this is a rule. I don't know if you call it a power in a power rule, but it's another version of the power rule. And so we have x to the m, but then that's raised to the nth power. You'll have x to the m times n. So I'm not sure what the name of that thing is, but it is a power rule of sorts. So it's like a power to a power, I guess you might call it, or an exponent to an exponent, maybe. Anyways, let me move on. As an example, if I have -2 to the 3rd, but I raise that to the 5th, then you can write this as -1. Well, I don't know if I want to do that. Probably not the -1. It's a negative number, so when you take it to the 5th power, it will still be negative. But I'll have 2 to the 3 times 5. So that'll be -2 to the 15th. Whatever 2 to the 15th is, I don't really care. I just want to exploit the rule. Let's see what else we could have. If we have z to the 8th to the 15th power, that's z to the 8 times 15, which is z to the 120th, I believe. We'll do a lot more examples later. Right now I'm just laying down the foundation for the rules. Most of the problems that we do are going to be a combination of these rules. Now check this out. If I have x times y, and I raise it to, say, the 5th power, I'll have xy times xy times xy times xy. How many did I put? 4. I need one more xy. So there's 5 of them. Now, according to what they call the associative property for multiplication, I can do this. That is, I can drop the parentheses. If you don't know, that was actually supposed to be a y in there. It kind of lost its way, but let me see if I can fix it. Now, the next rule I'm going to make use of is commutativity. So that means I can rearrange the order of this multiplication and put the x's first if I want, and then I can put the y's second. I do have an issue with drawing y's. I'm not exactly sure what my problem is with them, but nonetheless, I'll have x to the 5th power, because there's 5 x's up there, times y to the 5th power. So basically what I had is xy to the 5th. I could do x to the 5th, y to the 5th. And I don't know how important it is to remember. There were 2 things that I used, associativity and commutativity, for that to work. You can also, I don't think it's any stretch of the imagination to extend these to quotients or fractions either. But anyways, if I have xy raised to the nth power, I'll have x to the n times y to the n. And I have also indicated it, so I might as well write it. If I have x over y raised to a power, this will be x to the n over y to the n. This x over y, like if you do it to the 3rd power, you can see that you're going to have x over y times x over y times x over y. And when you multiply it out, you can see the rule applies just like I said. So I think these are called the product and quotient rules. So let me, product, I guess, there's, some of the names of these things are weird. Let me do some examples to illustrate everything we've got going here. All right, first, let me see if I have 4/3 times 4/3 squared, then I can rewrite this as 4/3 to the 1 plus 2, because the base in this case was 4/3 for both of them. The exponent on the first 4/3 was a 1. That's why I have 1 plus 2. So I get 4/3 to the 3rd, and then I can write this as 4 to the 3rd over 3 to the 3rd. Would be 64 over 27. All right, now let's get down to it. Now a bunch of examples utilizing these various properties. Typically, you'll be told to do this. Simplify, and they'll give you an expression and they expect you to know what to do. So I'll have x to the 6th power times 2y cubed times 3x to the 5th times 8y squared. Well, the way you can do this is you can rewrite it so that you can put the numbers in front, like 2 times 3. Then I can use the commutative property to write x to the 6th times x to the 5th. And then I can put the y's at the end if I want, y cubed times y squared. Now the 2 times 3 is easy enough to make a 6. The x's, I have x to the 6th plus 5. And for the y's, I have y to the 3 plus 2. And so that'll be 6x to the 11th, y to the 5th. The problem with exponents is initially they cause so much issues for students, but once you get the hang of them, I won't have to show as many steps for you to see how everything got there. So before I move on, I noticed that, I don't know if you noticed it here, I have my 2 and my 3, but what about that guy? I forgot about the 8. So let me see if I can sneak the 8 in there, put times around it. This 6 changes then. 2 times 3 is 6, but times 8 is 48. And then let me get that 6 out of there if I can and change it to a 48. And there we go. All right, let's move on to the next example. I have, I think, about 5 pages of these things. Let's see, simplify. Here I have negative 10p to the 8th times negative 3p. So as before, I'll bring the negative 10 times the negative 3 out front to get a 30. So that's where I got the 30 from, was I did negative 10 times negative 3. So typically I'll just combine the numbers right off the bat, if I can. For the p's, notice that there was a 1 as an exponent on that other p. So this is p to the 8 plus 1. That is 30p to the 9th power. For our next one, simplify again. This time we have 7/10 y to the 9th. I believe I got a lot of these out of the textbook. Times negative 2y to the 4th times 3y cubed. Now you ought to be able to tell if we have something with a positive sign, something with a negative sign, and something with a positive sign, we multiply them all together, you are going to get a negative answer for those things. Let me, as usual, put my numbers in the front. Took care of my numbers, and let me add up the y exponents. So I have a 9, I have a 4, and I have a 3. Between the 2 and the 7/10, I can cancel that 2 out and make that into a negative 7 over 5. And for the y's, I have an exponent of 16. And then one last step. If you think of that 3 as 3 over 1, you'll get negative 21 over 5 y to the 16th. Here's a quick one. Simplify. Here we have a raised to the 3rd power and then raised to the 2nd power. So this is like the product of a product rule. I'll have a to the 3 times 2 will be a to the 6th power. So you can see there's really only 4 rules that we specify here, but it seems like a lot more than that, especially with all these different problems. All right, let's try another one. Here we're going to have 5a over 2 raised to the 3rd power. So this, you just raise everything to the 3rd power. And it looks like we get 125 a to the 3rd power divided by 8. Oops. My next one, simplify again. Here we're going to have negative 7w to the 2nd power. So multiply everything to the 2nd power. So there's a negative 1 inside of there. I'll raise it to the 2nd power. You probably knew the negative would go away anyways. And then I have 7 to the 2nd, and then I have w to the 2nd. Well, the negative 1 is 1. The 7 is squared is 49. W squared. I'll end up with just 49 w squared. So in each case, you should be able to tell right off the bat whether the thing should have a minus sign in front of it or whether it should not. Let me do another one, and I'll show you what I'm talking about in this example here. here I have a negative, and then I have a cubed, b squared, all of that divided by c to the third power, and this whole thing is raised to the fourth. The negative, treat it as -1, so you'll have -1 to the fourth power. Then you'll have a cubed, but that will be raised to the fourth. B squared will be raised to the fourth. And c cubed will be raised to the fourth power. Well, -1 to the fourth is just 1. And then a to the third to the fourth is a to the 3 times 4. Then you have b to the 2 times 4 all over c to the 3 times 4. I can drop the 1, it doesn't do anything. I'll have a to the 12th, b to the 8th, all over c to the 12th. And this is sort of what I was talking about. If you know you have a negative and you're taking it to the fourth power, you know that negative is going to go away. So I don't know if I had to particularly write out this step, it may have made it more confusing. I don't know. Whatever the case may be, you can see the negative did go away because I raised it to the fourth power. Same with the last one. The negative went away because I raised it to the second power. All right, we're going to combine the rules. This is when, I don't know how many pages left I have, but I have a collection of examples here. Most of those previous problems were one step. They had one rule that we applied. This one will require several. I'll show you what I mean right on the first problem. So for this, we're going to have a to the 5th, but it'll be raised to the third power. And then we'll have d squared, but raised to the fourth power. What I want you to do, especially as I progress through these examples, is pause the video before I write the answer and see if you can get the answer before I do. And that way you'll experience the best possible result from this video process. For the a's, since it's a power to a power, I'll go a to the 5th times 3, and then I'll go d squared times 4. So I will have a to the 15th times d to the 8th. For my next one, simplify. And what do we have here? We have negative 5p q to the 4th times negative p to the 4th q, but that thing is raised to the 4th power. So I'm going to forget about taking -1 to the 4th, and I'll let you be able to handle this fact that -1 to the 4th will just go away, but this negative will not. This negative will be around for the rest of the problem. So let me have my 5p. I'm going to put a 1 above p to the 1 power, so it'll help me when I go and do the rest of it. Now we have p to the 4th raised to the 4th. So p to the 4th, that'll be raised to the 4th, and then q to the 4th. P to the 4th is p to the 4 times 4, and then we just have q to the 4th. So I have -1, p to the 1, q to the 4th, p to the 16th, q to the 4th. Now I'm simply going to move stuff around. So I put the p's together and put the q's together. So I can use this is the basic power rule, where you have the same base to two different exponents like so. So I'll add the 1 and the 16. And then the q, I'll add the 4 and the 4. So it looks like negative 5p to the 17 q to the 8th. Note. Take a look at this. 8 minus 5 raised to the third power. If you use the order of operations, then do the parentheses first, you'll get 3 raised to the third, and that will be 27. That is, of course, the correct answer. However, some students will get so confused by these rules that they may actually do this. This, of course, is very wrong. Look at what you get in this example. 8 cubed is 512, I believe. Minus 5 cubed is 125. And it looks like we get 387. Let me make sure, yeah, 387. You notice these things are vastly different from each other. This one is correct, the second one is wrong. So do not make that mistake. It will not work when you have anything in between there except a multiplication or a division sign. Anyways, that was just happened to be on my mind. Take that out of the picture and we'll move on. More simplifying. This time I'm going to have negative 2/5 z to the 5th to the third power. Well, hopefully you can see negative 1 to the third will be negative. So I'm going to take care of that right off the bat. Now for the rest of them, I'm going to have 2 to the third, 5 to the third, z to the 5th to the third. 2 to the third is 8, 5 to the third is 125, and then z to the 5 times 3. So I have negative 8 over 125, z to the 15th. Actually, that example was harder than that. I didn't write it all down. Well, I'll just make it into another example, that's all. So I didn't read my notes carefully enough. So I'm basically going to do most of the same thing again, except I'm going to add a little bit of it. We have z to the 5th to the third power, but then I had 10z to the second power. So let me go ahead and apply my rules. As before, negative 1 to the third power will still be negative. I'll have 2 to the third over 5 to the third, z to the 5th raised to the third, times 10 squared times z squared. So, and that one used another rule that was a product to a power rule. So I have negative 8 over 125, z to the 5 times 3, times 10 squared. Well, 10 squared is 100, so let me go ahead and do that. Times z squared. Let me put my numbers together, so I'll get negative 8 over 125 times 100, and then I'll have z to the 15th times z squared. Between the 100 and 125, I can cancel. 25 goes into 100 4 times, and goes into 125 5 times. So the 8 times 4, I'll get 32. Don't forget that negative is just hanging around. Negative 32 over 5, z to the 15 plus 2. So using the basic power rule for that part, we have negative 32 over 5, z to the 17th. So every single one of these has the same command, I guess you'd call it, at the beginning of them. That's to simplify. And you're probably going to see that these things are going to get more complex as I move on. So 2/3 d, and that's raised to the 8th power. Then I have 9/2 d cubed. That whole thing is squared. I did make a slight mistake here, so let me fix it before I go on. This is d to the 8th, but I wanted that whole thing raised to the 4th power. So let's go ahead and do these things. I'm going to have 2 to the 4th power over 3 to the 4th power. D to the 8th will be raised to the 4th power. Then I'll have 9 to the 2nd divided by 2 to the 2nd. D cubed to the 2nd power. Now let me go ahead and write these numbers out, what they're equal to. 2 to the 4th is 16. 3 to the 4th is 81. I am going to bring the other numbers out front. So this 9 squared over 2 squared I'm going to bring up next. That 9 squared was 81, and the 2 squared was 4. So make sure you keep this in mind. This piece here gave me 16 over 81, and then 9 squared over 2 squared gave me 81 over 4. For the d's, I have d to the 32 times d to the 6th. I'm using the power of a power rule for these two answers. Now there's simplifying that can go on. For example, the 81s just cancel away, but the 4 goes into the 16 4 times, so I have a 4 left over from all that. The d's, now that they're in the same base like this, I can add the exponents to get 4d to the 38. Simplify once again. This time we have negative v to the 6th times negative 2 v to the 5th, but to the 5th power. And then we have negative v to the 4th to the 3rd power. So first what I try to do is figure out the negative and positive. Let me do that. Here I've got a single negative sign, but then I have negative raised to the 5th power. It will still be negative. A negative times a negative will be positive. However, negative to the 3rd power is negative. So when all is said and done, I have 1, 6, 9. Negative 1 to the 9th power will end up just being negative 1. And you don't even have to write the 1 if you don't want to. Just put a negative. Let me take care of the rest of it. I have v to the 6th, 2 to the 5th, v to the 5th to the 5th, and I got v to the 4th to the 3rd. 2 to the 5th is 32. V to the 5th to the 5th is v to the 25th. V to the 4 to the 3rd is v to the 12. And now I'm going to put my number in the front, and I'm going to add up all of my exponents for the v's. So I had a 6, I had a 25, and I had a 12. So that looks like v to the 43rd. So negative 32 v to the 43rd. For our next one, we have negative 5 m to the 7th raised to the 3rd divided by 5n to the 12th, and that quantity is raised to the 2nd. So first of all, let me do my positive or negative. A negative raised to the 3rd is negative, and that's the only one I see around, so I'll just put my negative out front, waiting for the numbers to appear. Let me start with this piece up here. I'll have 5 to the 3rd, m to the 7th to the 3rd, divided by 5 squared times n to the 12th to the second. Now, as far as simplifying the number portion, the 5s, I think it's probably best to think of it this way. If you think of this on top as 3 5s and this on the bottom is 2 5s, you can it's probably not a stretch for you to be able to cancel 2 of those 5s and leave just 1 5 left over. So I'm going to do that. Now for the other parts, I'm going to get m raised to the 21, that's 7 times 3, and then n to the 24th, which is 12 times 2. And that will finish off the problem. All right, continuing on. Here I have 3x to the 5th, that's raised to the 3rd power, over 21 yz squared to the 6th power. So let's apply my power to a power rule and the product rule, all those combined. I'm going to get 3 to the 3rd, x to the 5th to the 3rd, and then below, the 21 is just going to hang around till the end of the problem. I'll get y to the 6th, z squared to the 6th. 3 cubed is 27, x to the 15 over 21, y to the 6th, z to the 12th. For the letters, I don't have any canceling I can do, but notice between the 27 and the 21, 3 goes into both of those numbers. 3 goes into 27 9 times, 3 goes into 21 7 times. So my simplified version of this answer is 9x to the 15th divided by 7 y to the 6th z to the 12th. Once again, let's simplify. Here we're going to have k to the 5th times k squared raised to the 3rd all over 7m to the 10th times 2m cubed to the 2nd. And let me handle the k's on the top first. I have k to the 5th, which was alone, so nothing happened there. But k to the 2nd to the 3rd will be k to the 6th power. And below I have 7m to the 10 times, so I have 2 squared times m cubed squared. Well, the k's, I can add the exponents to get k to the 11th on the top. On the bottom, I'm going to 7m to the 10th times 4m to the 6th. And I can multiply the numbers together. 7 times 4 is 28. And when I add the exponents on the m's, I get m to the 16th. And don't forget the k to the 11th in the numerator. Moving on. I think I may be on the last page here. There's another example. Let's simplify. Here we have negative 11 over 12 times 3 halves m cubed n to the 10th. So m cubed n to the 10th, and that's raised to the 2nd power. So I'll have negative 11 over 12 times 3 squared over 2 squared, that's raising those to the second power, m to the third squared, n to the 10th squared. So I have negative 11 over 12 times 3 squared is 9, 2 squared is 4. Then I'll have m to the 6th power. I'll do the 3 times 2 to get that 6. And then n to the 20th power. That's 10 times 2 gave me the 20th. Gave me 20. So any simplifying that I can do, the only thing I see is that I can cancel a 3 out between the 9 and the 12. And so when I do that, I actually should put what's left over, a 4 there. I put my negative. 11 times 3 is 33, and 4 times 4 is 16. And that is good. By the way, I just want to say something here. You could have written the same answer like this. You could have put all those letters in the numerator and just kept the 16 in the denominator. Either one of those are fine as an answer. After all, when you think of these things, if you were to work with them in fractions, you would think of them as being over 1. That would make them numerators. All right, here we have negative 7a to the 4th b divided by 8c to the 6th, and all of that is raised to the second power. So what I realize right now when I wrote my b is it has the look of a 6. So I'm going to try to make my b look as un-6-like as possible. Now the negative will go away in this problem because I'm taking everything to the second power, so no negatives. I'll have 7 raised to the second, a to the 4th will be raised to the second, and then b raised to the second. I have 8 to the second, c to the 6th to the second. And now I'm ready to use my basic, or the power to the power rules. 7 squared is 49. A to the 4th to the second is a to the 8th power. You multiply those times b squared. All of that. On the bottom I get 64. And I get c to the 12th. No simplifying could be done. Next one, we have 2p r to the 8th divided by q to the 11th, and all of that is raised to the 5th power. So not much here except raising everything to the 5th. So I get 2 to the 5th, p to the 5th, r to the 8th to the 5th, and in the denominator I'll get q to the 11th to the 5th. So power to power rules are applying for practically everything. The 2 to the 5th is equal to 32. P to the 5th really doesn't have anything to do. The r to the 8th to the 5th is r to the 40th, because that's the 40 is 8 times 5. And in the denominator we're going to do q to the 55. That's 11 times 5 gave me that. All right, let's see what we have in this case. We have 10 b cubed c to the 5th over 15a. All of that is raised to the second power. What I would do here, this is something you don't see very often, but students get so caught up in the rules that they may apply the rules immediately. And you can. It's just, notice this. Before I do anything, I notice that I can cancel a 5 out between the 10 and the 15. So I could really have a 2/3 there. So then when I apply everything to the second power, I'll get 2 to the second, b cubed to the second, c to the 5th to the second, and the same in the denominator. There was a 3 down there, so I'll have 3 to the second, and then I'll have a to the second. 2 to the second is 4. B cubed then squared is b to the 6th. C to the 5th squared is c to the 10th. In the denominator, I get 9a squared.